A laser cutter is a high-tech machine that factories use to cut parts out of metal. The traditional way to cut metal is with a stamping press, a slower process that requires a separate tool for each type of cut. A laser cutter's computer-guided beam can precision cut virtually any shape. A laser cutter is made up of a laser resonator, which produces the beam, and a mechanical system that moves the laser over the metal in a computer-controlled pattern. To build the laser resonator, they mill 2 blocks of aluminum. Each will hold a mirror on opposite ends of the resonator. They will reflect light back and forth inside the chamber to form the laser beam. All the parts go into a cleaning solution because any contaminants would shorten the laser's life. Assembly takes place in a clean room. After mounting the aluminum blocks onto separate aluminum tubes, they slide one tube inside the other. This forms the resonator's main structure. They install an electrical connector on one of the blocks. Then they mount a mirror onto each aluminum block. A generator pumps electrical energy into a pressurized mixture of gases, producing particles of light called photons. The mirrors at both ends of the resonator direct the photons back and forth, creating the laser beam. They now fill the resonator with that pressurized gas. It's a mix of nitrogen, carbon dioxide, and helium. For the laser beam to cut well, it has to be the right shape. But the beam is invisible, so to see its shape, they have to shoot it into a plastic cube and observe the formation it makes. They gradually fine-tune the beam's shape by adjusting the mirrors on the resonator. They keep at it until the laser cuts a cone formation in the plastic. On top of the tubes, they install a square housing containing a series of mirrors which further refine the beam. Meanwhile, a robotic welder fuses sheets of steel to construct the laser resonator's housing. On the main machine, these large suction cups move the sheet of metal to the cutting area. The sheet remains stationary, while a motion unit moves the laser beam over it. A rack and pinion system propels the motion unit. The system's racks must be perfectly aligned for the machine to cut accurately, so a technician uses precision measuring equipment to check the racks, then various tools to make adjustments. Once that's done, they set up the guide rails on which the motion unit rides, then mount the motion unit onto them. They bolt the motion unit to the front of the machine, and the housing that contains the laser resonator to the back of the machine. The resonator creates the laser beam. Mirrors deliver it to the motion unit's cutting head. Lenses inside the head focus the beam on the metal underneath. They run a series of tests to ensure the machine cuts with ultimate precision. It all boils down to whether the motion unit moves accurately, which means the drive system racks must be perfectly aligned. After testing, they enclose the cutting head with a safety cover made of sheet metal and plexiglass. The cutting head's copper-tipped nozzle emits the laser beam, while a curtain of brass pins confines that beam to a restricted area. The motion unit moves in 3 axes, enabling the laser beam to cut different thicknesses in 2 dimensions. A stamping machine leaves rough edges that workers must grind smooth afterward, but a laser cutter leaves a smooth edge that needs no further work. This saves on time and labor cost, making this technology a cut above.
Industrial cutting tools are the metalworking components of factory machinery. They're designed to form metal into product parts or into devices for making product parts. High-tech industries require high-precision cutting tools. These are end mills, tools specifically designed for cutting and shaping metal. They're made from a very durable grade of steel, or from tungsten carbide, a metal even stronger than steel. Steel bars in their raw state are actually soft enough to be cut and shaped, but it takes loads of lubrication to cool the intense heat that metal-on-metal friction generates. Using a giant bandsaw, they cut the bars into end mill-sized pieces called blanks. Workers turn each blank individually on a computer-guided metal lathe. First, they form a point on one end. Then they flatten the opposite end and drill a center hole. Then they trim the diameter to the required size. Next stop, a computer-guided milling machine. It works on 3 blanks at a time, carving helix-shaped ridges called flutes. The flutes run almost the full length of the blank. Once again, lubrication is essential to prevent overheating. This milling process transforms each blank into a tool. From this point on, the shorter smooth portion is called the shank, the longer fluted portion, the cutting end. Here's the same milling process again, but for a different model. Here are both models, before and after. Now they cure the steel using a 2-step heat treatment process. The first stage hardens the metal using molten salt that's been heated until it liquefies. They soak the tools in 5 progressively hotter salt baths, whose temperatures range from 650 to 1200 degrees Celsius. The second phase of heat treatment is a process called induction. They set each tool into a large metal coil. The coil's internal magnetic field generates intense heat, which softens the shank, making it more flexible. Now the finishing process. They run the shank against a grinding wheel whose grit is made of diamond particles. This gives it the strength to erode steel with a high degree of precision. They verify the final diameter using a digital micrometer. Then a robotic arm runs the tools one at a time through a high-precision automated grinding machine, this time to finish the cutting end. The machine uses diamond grinding wheels to grind the precise cutting angles and finalize the diameter. More complex tools go into this even more sophisticated grinding machine. It too uses diamond wheels and runs robotically. The end mills are now completed. This factory makes high-precision cutting tools primarily for the aerospace and automotive industries, where precision is everything. So at each stage of the production process, the factory verifies measurements using various optical and digital instruments. This sensing probe conducts the final quality control test. It scans each and every finished end mill to ensure that the surface is as smooth as silk. These high-precision cutting tools are now ready to be put to work machining aluminum, titanium, and different types of steel.